In this section, we talk about exceptions to the octet rule. There are three different types of exceptions to the octet rule, and I have them enumerated in examples here. The first one is compounds with an odd number. It's going to be an odd number. This one is nitrogen dioxide. We commonly would think of that as being a nitrite ion, but we're talking about the molecule instead. And so basically it has an odd number of electrons. This is one of the problems with the ozone layer, and as a green and destroying of the ozone layer. Most molecules that only have one electron are very unstable molecules. They want to react with something very badly, so they can pair up this electron. In nutrition, you'll hear the term eating an antioxidant. It's something that usually has a deep color to it. But basically, an antioxidant will give up electrons to the and so in nutrition we tend to call these the free radicals because they tend to be destructive to cell membranes and biological structures. And so an antioxidant then is something that will basically give an electron without destroying the molecule to a free radical, making it a more stable species. The second would be electrons with fewer than 8. So this is going to be metals and metalloids. Okay. This one, the sum of electrons are an odd number. This one is going to be metals and or metalloids, which are those molecules that are between the metals and the nonmetals. Okay, so boron trichloride is an example. Boron is right beneath aluminum on the periodic table, has 3 valence electrons, and so it doesn't need a C8. Okay, so it's when we try to draw Lewis structures for compounds that basically shouldn't be Lewis structures. And the last one is elements with more than 8 valence electrons. This is phosphorus pentafluoride, PF5. And just by nature, each one of these is 2 electrons, so this is 10 electrons here. So that's obviously more than 8. It doesn't have to be bonds. You can actually have some of these that have lone pairs that still have more than 8. So here's some structures, okay? And so I have the periodic table down here. I have chlorine, which is in group 7 or 17. So chlorine, there's 1. And because it's in group 17, is 7. Oxygen, there's 2 of them. And oxygen is in 16, so that's going to be 6 valence electrons to give me 12. And so when I add these up, this is 19. This is an odd, I don't want it that way. This is an odd number. So that means that this is going to be the first exception. Okay. So I draw chlorine in the center with 2 oxygens on either side, and by doing so I used up 4 electrons, leaving me 15. And then I draw 2, 4, 6, 8, 10, 12, 14, and then 1 more, and I just put that as a dot, not a dash. And I'm out of electrons. Chlorine only sees 7. That's going to make this extremely reactive. It's going to want to fill that extra electron there. Okay, so that was an odd number 1. Beryllium, and I want to point out where beryllium is. Beryllium is here. So being here on the periodic table, is this going to be a metal or a non-metal? This is a metal. So this is the less than 8. Beryllium is one of them, and it's in group 2A, so that's 2. Bromine there's 2 of them, and bromine is in 17, so it has 7 valence electrons to give me 14, so I have 16 total. Be goes in the center with Br on either side. So I used up 4, leaving me 12, and it's 2, 4, 6, 8, 10, 12. Okay, and because beryllium is a metal, it does not need to see 8. Okay. The next example is xenon, which xenon is a noble gas, so noble gases typically do not react. Okay, xenon, there's 1 of them, and each one has 8, so that's 8. Fluorine, there's 2 of them, and fluorine is in group 17, so therefore it's 7 to give me 14, so that's going to be 22. Xenon goes in the center with a fluorine on either side. Okay, so I used up 4, leaving me 18. So I go 2, 4, 6, 8, 10, 12. That still leaves me 6 electrons. Where do those 6 electrons go? Well, this fluorine sees 8, this fluorine sees 8. So the answer is on the central atom, but not shown as a bond. Okay, so you see here I have these drawn. They are, again, if you put this imaginary circle, if you put an imaginary circle around xenon, they are parallel or laying on that circle, whereas a bond is coming off of that circle. So the things that I would not show would be, sorry for the phone call, answers that are not acceptable. For this one would be xenon, double bond fluorine, double bond, and I still have to have a lone pair. Okay, that's not acceptable. So not acceptable. I do not want to see these. I don't really like seeing them like this. Okay. And that's my husband leaving me a message. Sorry about that. So again, they should not be drawn off looking, to me, these look like bonds. I don't want them to look like bonds. I want them to be parallel to or laying on that imaginary circle, if you will. So neither one of these answers would be acceptable ways of doing this. But this fluorine here sees 2, 4, 6, 8, 10. So this one has 10 electrons around the center. Okay, and the last one that we will do is going to be, let's go back to blue. Sulfur. Okay, sulfur. There's one of them, and sulfur is in group 16, so that's 6. Gives me 6. Fluorine. There's 4 of them, and we did this up here at 7 because it's in 17. So 4 times 7 is 28. So that's going to be 34. So I have sulfur in the center with 4 fluorines. So I used up 8 when I did that, and that's going to give me 26. And then I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I used up 24 that way, but I still have 2 more. Again, I don't want it to look like a bond. I'm going to draw it here. You could draw it here. You could draw it here. And you could draw it here. My fluorine, this bond is not really looking very good because it's not there. But I could draw it here or I could draw it here. Okay, so any of those would be acceptable. But again, this one's an example of seeing 10. And we can see up to 12 electrons on that central atom. And so that is the end of this section.